Let's do our review problem. So we have the following question. Convert the integral in cylindrical coordinates to an integral in spherical coordinates. And we see z, r, and theta. It's like, okay, that feels very cylindrical-like. And we have various bounds. And we have some options here. And all these involve rhos and phis and theta. So yes, these all look like spherical coordinate integrals. But which one is the one that matches? In other words, which of the 5 corresponds to the exact computation that the original integral asked us to do? So, do we have an answer? Did anybody say, aha, I see it? C? It's not C. B? It's not B. A? It's not A. D? It's not D. You're right, it was E. That was great. Amazing. Beautiful. Okay, so let's talk about it a little bit. So, okay, so what are some things we see? We see theta going 0 to 2 pi. That indicates we go all the way around. So the only place theta shows up is here, and we're going 0 to 2 pi, so full revolution, so great. So now we say, well, to understand what's going on, instead of trying to draw things in 3 dimensions, which is tough, let's look in a slice. So we look in the RZ plane. So we see 2 lines, z equals r, which goes straight up, and z equals root 2 minus r squared, which is really a circle. So we're going from the circle up to the line. So this little shaded blue region here, that's what you would take and spin it around the z-axis, and that would form your shape. Well, it turns out that they intersect at 1, almost like it had been planned to happen, because it was. And all right, so what can we say? We know our theta bounds because theta represents the same thing in both spherical and cylindrical, so that doesn't change. What about our phi bounds? Well, you have to remember how phi is formed. Phi says 0 is pointing straight up the z-axis. We don't hit anything until this line, z equals r. That's 45 degrees, our pi force. And then we are hitting our region, hitting our region, hitting our region until we're at a 90-degree angle, so that's pi halves. Now, just that, if all you know is your phi bounds, you can narrow your choice down to either B, C, or E, because those are the only ones with the right phi bounds. So that gives you a 1 out of 3 chance. Now, that means you have to understand where phi measures. If you thought phi equals 0 is here, then of course you'd be misled. What about your rho bounds? Where rho comes out from the origin, you go until you hit what would be the sphere, and you stop at what would be the cylinder. So the sphere is radius root 2, so your bottom bound should be root 2. Your top bound is where you have r equals root 2, but r is rho sine phi. Solve for rho, you get root 2 cosecant phi. And then at this point, you're like, cool, you've narrowed it down to 2 options. So C and E are your 2 options. So, okay, now we've got a 1 in 2 chance. But that's the bounds. What's going on the inside? Well, here's the part where you have to be careful, because you have to switch your dv. There's no r. And that's where a lot of people might have been misled. It's like, well, there's no r, so what do? You add an r. You can't just add an r, can you? Well, you can if you balance it out. So in this case, you're multiplying and dividing by r, which is equivalent to times 1. Times 1, you're allowed to do. So the r dz dr d theta, that's your dv. That becomes your rho sine of phi, d rho d phi d theta. Then z is rho cosine phi, r is rho sine phi. And so the signs cancel. That's why there's no sign here. And then you end up with 1, 2, 3, 4, subtract 1, so 3 rows. So you get rho cubed cosine squared. So E is the right answer. All right, good. Good. Well, a nice practice. Perhaps that's an indication. Maybe you should practice a few of these. Don't worry, there's plenty of problems to come. Yes?
How did you know E is pi over 4? Like, how did you find that value?
Well, so that comes to saying, think about everything from the origin. Start here, and you start pivoting. You pivot. You pivot. It's like you're taking a couch downstairs. Pivot, 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 until what? Until you hit the region. So I'm hitting the region at this line. So that's where my phi starts. So I start at pi over 4. And then you keep pivoting. It's like, I have my region. Woohoo! Region, 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 region. Oh, stop. And that's when we end, and we say, how far have we moved? So pi over 2. So yeah, I mean, this is a great time when like a pencil or pen comes in handy, because you just sort of think about turning and how far you've gone. Other questions? Yes?
I think I understand this question. How do you know for a fact it's pi over 4? Like, looking at it, how do you know that it's pi over 4?
Because I'm a good artist. No, okay, so if you look at this, we have z equals r. So what we can do is we can always draw triangles. And so if I have z equals r, if I have r goes out 1, then I have that z goes up 1. Now, that's not the triangle I want to look at, because that's not where phi is. Phi is over here. But that's okay. I can just translate. So that says this distance is 1. This height is 1. It's a right triangle. And so I say, there's a right triangle where these two sides are equal. That must be a 45, 45, 90. All right? Cool. Okay, so thought for the day. Arthur Ashe, tennis player. You start where you are, use what you have, and you do what you can. And sometimes we feel like, I have to wait. I can't start doing something today. I have to wait for something important to happen. You know, a certain date must come, or a certain event must occur, and only then can I start studying or preparing. No. Start now. Wherever you are, whatever you have, start. You're much better off. You know, there's that classic saying, the best time to start studying for a calculus exam was at the beginning of the semester. The second best time is today. Actually, that's not the saying. It's, the best time to plant a tree was 20 years ago. And the second best time is today. But I thought, calculus exams, that's more on people's minds right now. So, all right. So, what's today? Well, I already mentioned we're moving towards vector calculus. And the idea of vector calculus is we're going to talk about vector-valued functions. And so I didn't want to have to draw a lot. So this is a time when I cheated and I let the computer do the drawings. And but what is a vector-valued function? We understand what functions are. They're like machines. And they're rules. And it says, okay, you plug in a number or possibly several numbers, and something happens, and out comes a vector. We have seen these already, so they're not completely new. When we talked about motion, we said, well, we're going to represent motion by vectors. And why? Well, because we can do calculus with vectors. We can't do calculus with points. So we went from thinking about describing location by a set of coordinates as points. We said describe location as a vector. Another important vector that we've seen is the gradient. And the gradient stores a lot of information about what's happening to the function. Now, one thing you might notice is whereas with motion, you have just a single input, which is time. With the gradient, you can have multiple inputs, which is location. So vector valued functions can have single inputs, multiple inputs. It just depends what you want to know. Now, these are sometimes called vector fields. And they're visually represented by a collection of vectors, which you look at sample points. Now, the reason we have to do something to represent it is it's hard. How do you plot a vector? How do you draw a vector? And whereas with surfaces, you can say, oh, I'll just put an elevation. I'll do that at every point. Well, how do you draw a vector at every point? And you really can't. So instead what you do is you say, well, let's just pick a bunch of points, and let's draw what the vector would look like. And so we'll do this and see what's going on. So, for instance, suppose we have our function f of xy is the vector valued function xy. So that means if I'm at a point, let's say I'm here at this point, and let's say this is at the point x equals 1, y equals 1. What would be the vector? Would be 1, 1. Well, that says go 1 in the x direction, 1 in the y direction, so your point in that direction. So what you're doing is you're collecting these vectors. Now, maybe we'll try something a little bit more exotic. Well, let's suppose we're down here. Yx. And again, we'll pick a point. Here's a point where we look like roughly we're at the point -1 comma +2. So then if we take that point and we plug it into the vector valued function, according to this, it says that produces a vector 2 comma -1. So what does that vector do? Well, it says go down 1 in the y direction, over 2 in the x direction. So that's why you see this vector pointing in that way. And you just do it again and again and again. Computers love these things. Now, humans, not so much in plotting it, but visually, we're okay with it. It gives some insight. Now, you might have seen things like this before. For instance, sometimes you have weather maps that talk about the wind. So how do you mark the wind? How do you represent it? They're vectors, right? Because you have a direction. You also have a magnitude. So you represent the direction by an arrow. Now, how do you represent magnitude? Well, there's two ways to represent magnitude. Now, one way, which is what's done in this collection, is the bigger the vector, just put a longer vector. Now, that can be very tricky. So oftentimes when you see wind, what they'll do is instead of making the vectors longer or shorter, they'll make them bolder or thinner. So depending upon the thickness, it represents a different type of magnitude. And visually, you say, okay, well, there's lots of fun things going on here. You can almost play a game of connect the dots, where it's like, well, this is telling me something about how things move. And there is some truth to that. And we'll get to some interpretations of what we think of as vector-valued functions later on in the course. On a side note, there was at least one exam in recent memory where one of the things they did is they said, here's a picture, or here's a collection of pictures, play the matching game. Now, how do you play the matching game? What do? Well, guess is a strategy, but it's not a very good strategy. So what you can do is you say, look, I don't have to plot everything. Just pick a couple points and say, what if I'm, say, over here? Just try to say, like, x equals -3, y equals +3, and say, which way is the vector pointing? Which way should it point? And say, does it match the situation? And so what you can do is you can do a process of like, this is consistent with what it says it should do in terms of direction. And if it's not matching with direction, you can eliminate. So you don't have to do the whole thing. Just pick a couple points and ask, is my vector pointing the right way as to what the picture says? And if it isn't, then that's not a possibility. All right. Well, one classic example of vector-valued functions are force. So force has a direction and it has a magnitude, and so that leads to force fields. So here's an example. Let's say the following is a force field. So I have a function of xy, and it's written as minus kxi plus yj over x squared plus y squared to the 3/2. And we'll do a rough sketch of what this says. Now, it may not be immediately obvious what this function is. So we can try to first understand the function, or we can just plot some vectors. What should we do first? Understand? Plot? Well, okay. Let's think of it for a second here. This is using the I and j notation. So remember, that's just another way to write vectors. So this is the same as negative k x y over x squared plus y squared to the power 3/2. So, not drawing anything yet, I have a point here, x, y. Now the question is, which way am I pointing? Roughly speaking. Any intuition? All right, I hear some answers: away from the origin, to the left, up, down, towards the origin. Okay, so let's make some notes. This vector, to begin with, is the vector x comma y. So if you start at the origin and point to the point, that vector that does that is just put in the entries of the point. Now let's look at what's in front here. So x comma y, if we didn't see anything else, x comma y would point towards the point, and so if we just moved it, x comma y would point away from the origin. Now, but we have some stuff here. Can we say anything about that term in front? What does it tell us? It's a negative. What does that do to your vector? Flips it around. So now, where are we pointing if we flip it around? We're now pointing towards the origin. So if we're at any point, we point towards the origin. Okay, so that's something. We know we point towards the origin. That roughly gives us a sense of direction. Now what about magnitude? Well, oftentimes with magnitude, it's helpful to think of things in terms of magnitude times a unit vector. So suppose we wanted to make x, y into a unit vector. What would we need to divide by? The magnitude of the vector, right? The square root of x squared plus y squared. Yeah. So we can think of this as negative k over, and then we'll leave some stuff here, xy square root of x squared plus y squared. So this is our unit vector. And then what's left over? So we have x squared plus y squared to the half. Here we need to get x squared plus y squared to the 3/2. So we're left with x squared plus y squared to what power? To the 1. All right. Well, so let's think about what this says. What happens if we're far from the origin? So if I'm way out here, is my vector a long vector or a short vector? Short. Why? Because x squared plus y squared is big. if I'm near the origin, am I a big vector or a small vector? Long or short? You're longer, right? So in fact, what we can say is this is k means proportional. And now, if you think about x squared plus y squared, that actually has a fun name. This is the square of the distance to the origin. Okay, so roughly speaking, we have little tiny arrows far away pointing towards the origin. But as we get closer, our arrows start to get bigger. And of course, things get really crazy if we're very close. So, do we know any type of force which scales proportional to the inverse square of distance? Yeah. This is gravity. So, gravity. Unfortunately, I don't know the songs to Wicked well enough to sing, but so that's gravity. And notice it didn't say a good sketch, just said a sketch. So there we go. All right. It's one of the reasons why we never ask you to sketch a force field. We only ask you to identify them. Okay. Now, there's a special case of vector fields. If I have a vector field, so I'm going to use capital F for a vector field, if it's the case that it's equal to the gradient of some function, then we say that F is conservative. Now, that doesn't mean that we're asking F its opinion on taxes. It's just a different type of conservative. That's no politics in this. All right, so F is conservative if it's the gradient of something. Little f is called the potential function. Now, how do we think of this, our intuition? Our intuition in this part of the course is that what you see here, which is usually called del, in some places it's called nabla, and we're thinking of that as taking derivatives. We're going to talk a lot more about that in just a few minutes. So I say, so capital F is the derivative of little f. So in some sense, little f is like the antiderivative. So being conservative is special. Most functions are not conservative. You want conservative functions. And why do you want conservative functions? Essentially, if you are a conservative function, because you have that antiderivative, nice things happen. And that's the punchline that's going to be here at the end of the week. Nice things happen if you have conservative functions. All right, so let's do a quick example. So here's a function. Now, you can always make conservative functions. That's super easy. Just pick your favorite function of x and y and take the gradient. You've got a vector field. That vector field is guaranteed to be conservative. So we're going to make a conservative function. All right, so here we go. This is a reminder. How do we take gradients? All right, so our function is f of xy is some constant k, x squared plus y squared to the minus 1/2. So gradient of f, let's just first remind ourselves, what goes in the first slot? Partial with respect to what? X. Partial f, partial x, and then in the second slot? Partial with respect to y. Partial f, partial y. So that's what the gradient is. Well, so that says we're going to take the derivative with respect to x of, and I'll just write down our function x squared plus y squared to the minus 1/2. And then we're going to take the derivative with respect to y. Again, write down our function x squared plus y squared to the minus 1/2. And there we go. All right, so now practice taking derivatives. The constant just comes along for the ride. What happens next? Chain rule. Okay, so what do we need to write down next? Negative 1/2. And then? Well, x squared plus y squared to what power? Negative 3/2. And then? The 2x. So we do need the chain rule. Comma. What comes next? Okay. Negative 1/2. X squared plus y squared to negative 3/2 and 2y. Well, they have stuff in common. We'll notice a few things really quickly. The 2 and the half cancel in both cases. Let's factor out the common stuff. They both have a negative. They both have a k. Right, there's negatives, they both have k. What else do they both have? Yeah, x squared plus y squared to the 3/2 in the denominator. What's left? In the first slot? X, second slot, y. Does that look familiar? What is it? Gravity. So this shows that gravity is conservative because it has a potential function. All right, good, good. Well, now, any questions so far? All right. So we want to talk about del. So we're going to think of del as the del operator. Now, what is an operator? An operator is basically something that will take a function and it makes a new function. So it's a lot like a machine because it's doing the same thing. You have an input, you do something, you need to get an output. And so if we're thinking of del as like our derivative, we're like, well, the derivative is an operator. You start with a function, you take a derivative, you get a new function. So what does del look like? Well, it depends on what dimension you're in. If you're working in 2D problems, you have your partial x, partial y. In 3D, partial x, partial y, partial z. So del is the collection of partial derivatives. Now the question is, well, how do we take that and apply it to a function? Well, it's a vector. We think about, well, there are ways for us to combine vectors together. And in particular, there's 3 types of vector multiplication. There's scalar, which means I multiply a vector by a number. So I'm going to put number in quotes here. There's a dot product. What happens with the dot product? Do you remember? Vector dot vector means you multiply the corresponding entries and you add them up. If you multiply 2 vectors together using the dot product, what's the output? A scalar. Then there's the cross product, which of course is always everybody's favorite. Now there's a note here about the cross product. It doesn't always work. What needs to be true? You have to be in 3D. Cross product doesn't work in 2 dimensions, doesn't work in 4 dimensions, doesn't work in 17 dimensions. It works in 3 dimensions. But very conveniently for us, we spend a lot of time in 3 dimensions, so we know about 3 dimensions. We're somewhat comfortable, you might say. All right, so because there's 3 types of vector multiplications, there's 3 ways we can use our del operator. So let's go through them. Number 1, the scalar product. That's the one we already know. That's the gradient. So the gradient of f is scalar multiplication. So we're taking our del operator times f. You take your scalar function in, you get a vector valued function out. That's all I have to say because we've already spent time talking about the gradient. Are you comfortable enough? Do you need to see an example? Or are you like, I know how to do a gradient? You know? Okay. All right. Because the fun stuff's coming up. All right. What's the second type of product we mentioned? Dot product. Okay, here's where things get interesting. New stuff. Dot product is divergence. Sounds like it should be a young adult dystopian novel. All right. So what is divergence? Just think of it as del dot f. What happens? You're going to put a vector valued function in. You're going to get a scalar function out. So how does it work? So I'm putting a vector valued function in. So I'm thinking of MNP as the individual entries in my vector. So each one of these is its own function. So the divergence of MNP says take the del, partial x, partial y, partial z, dot it with MNP. That gets you partial m, partial x, right? Take the first two, partial m, partial x, plus partial n, partial y, plus partial p, partial z. This is probably everyone's favorite because it's relatively straightforward, no surprises. And there's a beautiful fact. We're introducing these because every single one we talk about has applications. We've seen gradient applications. We're going to see divergence applications. We'll have another one we'll talk about. We'll also see applications there. Every one of them, essentially, what we're building up to is we're going to be doing fundamental theorem of calculus stuff. That's our goal. And so there's several themes, and we're basically saying, let's talk about what derivatives look like. That's what these del operations are doing. Okay, so let's make up an example. So let's make a vector valued function f. You want 2D or 3D? I wrote 3D, but 2D works as well. Going 3D, someone said. F, x, y, z. Okay, what function do you want in the first slot? 4x cubed. All right, what function do you want in the second slot? ln of y plus z cubed. The third slot, sine of xz, and I don't have enough space, but I want to say plus arctangent of xy to the x squared cosine y. Okay, right? Hold on. I know you're skeptical, but I want to point out why we love divergence. So let's take it. Del dot f. Okay, what do you do with the first entry? Take the derivative with respect to x. Oftentimes we don't write this, but I'm going to go ahead and do it right out now. What do we do with the second entry? Derivative with respect to y of the second entry. And we don't have enough space, so I have to go to the new line. And the third entry, derivative with respect to z. Oh, someone said, oh. It's like, oh, I see what Steve did there. He wanted to appear mean, but he just can't do it. He doesn't have a mean bone in his body. All right. What do we get? The first derivative gives us 12x squared. The second gives us 1 over y. The last one gives us derivative of sine x cosine xz. And all of this, which looks terrible, goes away. It's 0. So oftentimes we can write problems where the divergence is involved, and we can write these really ridiculously over the top, like, I don't even want to touch this function. And that's the clue that you shouldn't do it. You should use the right tools so that things become like, oh, that's a nice function. you know, I may not take that function home to meet my family, but you know, I exchange postcards every year. So divergence, that's not so bad. All right. Are we good with divergence? We'll get more practice with it. Okay. Last one. Oh, yes.
What's the difference between this and a gradient? Because I'm just taking a derivative.
So what's the difference between divergence and gradient? Well, part of the difference is, think about what kind of function you have. So if we pull up, it is true we are taking derivatives. So if you compare gradients to divergence, we see that the inputs are different. Whereas gradient says start with a scalar function, divergence says take a vector valued function. And then what happens is the outputs are different. In gradient we have a vector valued function, divergence we have a scalar function. Another difference is it is true that we're using partial derivatives because the del is always about partial derivatives. However, you'll notice here we're taking different partial derivatives of the same thing. So it's partial f, partial x, partial f, partial y. On this case, we're taking different partial derivatives, but each one is also attached to a different slot. So partial m partial x, partial n partial y, partial p partial z. So there are differences. All right. What's our last vector product? Cross product. Yes. All right. And that has a name. That's called the curl. Curl of f. So curl of f is del cross f. Now what does this do? It's going to take a 3D vector valued function, and you're going to run it through the system, and you're going to get a 3D vector valued function out. So how does it work? Well, it's a cross product. So you have your curl of m and p, and so that says take your collection of partial derivatives, cross your vector valued function, and the way we do our cross product is as a matrix. And in the first row, we write down our I, j, and k. Our second row is the first vector. So that's partial x, partial y, partial z. And our last row is the second vector, m and p. Now, this is perhaps one of the strangest things you might encounter if you start to think about it. And so I encourage you not to think too hard about it, but rather just say, I have a rule. Now, why do I say it's strange? Let's think about the objects. What are the objects in the first row? Yeah, they're vectors. In particular, as someone said, unit vectors pointing in different directions. What's the objects in the second row? Yeah, these are derivative operators. So they're not functions. They're things that do things to functions. What's the entries in the last row? Those are functions. So these are just like a weird mishmash of all these different types of things that all come together, and you're like, what? Can this have any possible meaning? Yes. And so roughly speaking, there is an idea that curl can be thought of as measuring the rotation, what's going on locally. We won't get too much into that, but there is a geometrical meaning here. Now, how do you actually compute this? Well, you just do your diagonals, right? So for I, partial y of p. So that's p sub y. So this indicates the derivative of p with respect to y. Then in the other case, you're going to have, in the other direction, n partial zi. So that's where you get your nz. But it's subtracted. And you just go through and you do it for every single entry. Now, I don't memorize this formula. I memorize the determinant. And I just run it through every single time. That being said, we will see these pieces showing up. And in particular, there will come a time next week when we're going to see this expression, and you're going to be like, huh, have we seen anything like that before? And someone will say, oh yeah, Steve said we're going to see, there's a time next week when we're going to see this expression. And Steve's going to ask if we've seen this before. And I'm going to be the one that says, that's a curl. It's like, yeah, that's curl. It's the third entry of curl. So you will see hints of things coming in the future. Okay, well, we should do an example, right? All right. Now, whereas with divergence, you can go crazy, with curl, it's also possible to go crazy, but you have to do it wisely. All right. So, shall we make up a function? What do you want our vector valued function to be? First slot. Make x. Okay, if you're going to say x, then I'm going to go ahead and say, let's have fun with that. Cosine x to the x plus, what's another fun thing? E to the x. There we go. Plus y. Okay, second entry. Now, because I wrote that down, what does that tell you is going to happen? It's got to go away, right? Now, do you think that's true? Let's look at m for a second. Where does m show up? Those two places. What kind of partial derivatives do you care about? Y and z. What do you see here? Just x. So that's going to go away. So that's how you can throw some crazy stuff in, but you have to know how to do crazy stuff. Okay, second slot. We'll be simple from now on. What? Why are we going to be simple from now on? Because I like you. I don't want bad things to happen to you.
7y to the third plus xz.
Okay, plus xz. Okay. Now you might say, why didn't you take the 7y to the third? Well, what's going to happen with that 7y to the third? It's going to go away. Anything which only depends on y in the y slot will disappear. Just like anything that depends just on x in the x slot disappears. All right, the final slot.
Z to the z.
We already have an x to the x, you know. We're variations on a theme. I mean, yeah.
Cosine of x times
Arctangent of secant? I've raised these kids well. Okay. Sine of y. All right. I know. Steve's, where's his profile and courage? I don't know. Okay, so, all right, so let's do this. Curl of f. So we're going to set up I, j, k, partial x, partial y, partial z. There have been, by the way, tests where the questions are, just compute the curl of this. So you just want to make sure that you can actually carry through this computation. It shows up naturally in some problems, and sometimes we're just flat out, we're going to ask. Okay, so let's start going on our diagonals. Partial y of sine y. Cosine y. So that's in the I direction. So cosine of y, I. J, partial z of cosine x to the x plus e to the x plus y. 0, because there's no z. So this is partial z of that expression. So 0j, don't worry, we have more for j coming up. K, going down the diagonal, partial x of xz. Z, so that's plus zk. And remember, we're going to go down our diagonals, but then we're going to go up and subtract. So, going uphill, we're going to subtract the derivative with respect to y of cosine x to the x plus e to the x plus y. 1. So subtract 1 times k. going up. Partial z of x times z, that's going to be in the I direction. So what do we have? X. So minus xi. And then last thing we have sine y, partial xj. So, okay, partial x of sine y? 0. And that's in the j direction. We're going to subtract that. Now, I didn't line things up great here, but in the first slot, what do we have? Cosine of y minus x. The middle slot, what do we have? 0. That can happen. The last slot, what do we have? Z minus 1. Okay, so we can do curls. I probably should write the word curl and not cur. So that sounds a bit curmudgeonly. All right. So find the following. The curl of the gradient of f of x, y, z. Oh, this is fun. Okay, so first off, what will we'll do the first one. Curl, the gradient will give us a vector valued function, which we can think of as f sub x, f sub y, f sub z. It's a collection of partial derivatives of f, yes? So that's I, j, k, partial x, partial y, partial z, f sub x, f sub y, f sub z. True? Okay. So I, partial y, f z. So that's f z y in the I direction. J, partial z, f x. So that's f x z in the j direction. K, partial x, f y. That's f x y in the k direction. So far, so good? But now we get to subtract. We have partial y of fx minus fxy in the k direction. Partial z of fy minus fzy in the I direction. And then partial x of fz, that's minus fxz in the j direction. What does that give you? 0. So it's always the case that the curl of the gradient is 0. By the way, if something is a gradient, we had an earlier name for it. What kind of functions are the gradient of something? It's kind of like, it's tied to that. They're not liberal, they're conservative. So the curl of conservative functions is 0. What? That's crazy. Now, if we had time, but we only have like 30 seconds, we'd run through. Any guesses what the divergence of the curl is? 0. Coincidence? No. No, there's some beautiful math going on there. All right, that's it for today. And we'll pick up again next time.